Hello. Okay, so we will proceed to our discussion uh, of multivariate analysis, and this time we will proceed with simple and multiple linear or simple and multiple regressions, particularly the linear regression model. Okay. So recall, okay, our concepts of theory, proposition, and hypothesis. So in regression analysis, you just don't do regression analysis without theoretical basis for your chosen variables and their relationship, except if you are doing the stepwise regression analysis, which I'll be discussing later. Okay. So in the end, okay, the relationship and the degree of influence of the independent variables are predictors to your dependent variable requires theoretical basis or theoretical framework. That's your contribution to the expanding body of knowledge and to the decision-making process when you apply a certain theory in a specific context. That's how the theory is confirmed and being expanded in the process. So suppose you have a theory and it says that intelligence leads to success. Okay, so you want to argue or you want to um, come up with a proposition or an argument associated with the theory with this theory. So suppose if intelligence leads to success, then you have in mind that intelligent individuals should be having financial success in life as well. So that's the reason why you have formulated down to your hypothesis that IQ score affects an individual's income. So this is what you're going to test now. If IQ score affects an individual's income in relation to your theory, which says that intelligence leads to success. So you are employing or applying this theory in the context of, individual financial success or financial aspect or of life or in the financial aspect of life. So you might come up with this kind of simple linear regression, okay, associating IQ score to income. If it has a specific level of influence to your income. If your IQ score has a specific influence to your income. So as a result, you will come up with a model which look like this, no? Y is equal to C plus BX, where C is the constant, B is equal to the slope or the coefficient, and X is your IQ score and Y the income. So you will place values for your X and Y here. But of course, since your Y is dependent to your X, so whatever value you will place here in your X will be, will reflect on the value of Y. So now I'm giving you this analogy here, okay, before we proceed to our discussion, more discussion about uh, regression. So you have two types of tools here, and each of these tools are used, okay, when you are, in the kitchen. Of course, you will be using those tools associated with, cooking. And if you are in carpentry, you will use those tools, okay, associated or helpful in doing carpentry stuffs or matters. So it's the same analogy in doing multiple or doing linear regression or any regression analysis, because this is a tool, a statistical tool that you cannot just use, okay, whenever you want it, because there are certain assumptions. So just like the tools in the kitchen, you cannot just use it whenever you want to use it, but you're not in the kitchen. So the assumption there is you must be cooking or doing something, okay, for you to be able to use this tool. So it's the same analogy, okay, with regression analysis. So there are assumptions before you can use them. There are assumptions that you have to satisfy. okay, like variable types, the dependence, sample size, multicollinearity, independence of error, outliers, normality of errors, homoscedasticity, and linearity. So these are the assumptions of multiple linear regression, but we will be discussing some important assumptions here. So like the linearity of the phenomenon measured, constant variance of the error terms, or we call it homoscedasticity, independence of the error terms, normality of the error term distribution, and no multicollinearity among independent variables. So this is an example of, a linear pattern. So there must be a linear pattern between these two variables here, the length and the chest of, I think the chest of someone or individuals. So the chest and the length, okay? So there must be a linear association here, okay, by just simply looking at the scatter plot. Okay. So this is the kind of relationship we are looking forward in order for us to use linear regression. Okay, because in the first place, we are looking for the linear association between the variables here. So it would not be fair if we are looking for a linear association between two variables. However, they don't have in reality or in actual, they don't have a linear relationship. What if they have exponential or logarithmic or other form of, pattern, not linear pattern. So in case, okay, if linearity is not met, so we can do some remedies here, okay? We can transform or transforming the data values, we can apply logarithm, square root, and others, okay, of one or more independent variables to achieve linearity. And we can also directly include the nonlinear, or we can use, nonlinear relationships in the regression model, such as through the creation of polynomial terms. So another is we can use specialized methods such as nonlinear regressions specifically. So do not focus on, perhaps it's time that you have to leave linear regression, but you can move to nonlinear regression, specifically designed to accommodate the curvilinear effects of independent variables or more complex nonlinear relationships. So another is we have constant variance of error terms, or we call it homoscedasticity. So here in this scatter plot, you can see the other side, okay, from the other side, you can see homoscedasticity, and the other side, you can see heteroscedasticity. So that's how it looks like, okay? What is this? Actually, homoscedasticity is when you plot the predicted dependent values and comparing them to the null plot, uh, or yeah, it's actually plotting the residuals against the I'm so sorry, it's plotting the residuals against the projected dependent values, and so you can compare them to the null plot, and it shows consistent pattern if the variance is constant. So in this case, the variance is more constant in the red plots compared to the blue or green plots, because there's what we call consistency of variance. Okay, when you plot the residuals, okay, this when you say residuals, the standardized residuals, this is the difference between the predicted value and the predictor. Okay, I sorry, the actual value and the predicted values. Okay, so that would be the residuals. So the error term. Okay, so you can plot it this way. So in SPSS, you can use also Levent test for homogeneity of variance, or use the available scatter plot for residuals and predicted dependent values, okay, just to find out or detect homoscedasticity. Now, the contrary to homoscedasticity, we have heteroscedasticity, which is actually the variance of the error terms are not the constant but varied, no? So that is heteroscedasticity. Now, what are the remedies? Of course, if the violation can be attributed to a single independent variable through the analysis of residual plots, then the procedure of weighted least squares can be employed. On the other hand, employ variance stabilizing transformations that allow the transformed variables to exhibit homoscedasticity and be used directly in the regression modeling. So another is we assume independence of the error terms, okay, when we use especially multiple linear regression. We assume in regression that each predicted value is independent, which means that the predicted value is not related to any other prediction. That is, they are not sequenced by any variable. So this is how we can identify, no? So the independence of the error term. So we can best identify such as occurrence by um, plotting the residuals against any possible sequencing variable. So if the residuals are independent, the pattern should appear random and similar to the null plot of the residuals. Violations will be identified by a consistent pattern in the residuals. So just like this one. Okay, so we can see there that the other one, okay, that's not independent, and the other is independent. So we're looking for that one, okay, the independence of the error terms. So the remedy, of course, you can proceed to data transformation. If we found there's an independence of the error term or the independent in there's what we call dependence of error terms. So we can do data transformation such as first differences in a time series model or inclusion of indicator variables or specifically formulated regression models. Another assumption is the normality of the error term distribution. So this talks about the normality of the independent variable or dependent variables or both. And SPSS, for instance, use a normal probability plot to detect this, or you may employ statistical tests such as Kolmogorov-Smirnov test or Wilk-Shapiro or Shapiro-Wilk test. So this is how, if you're using the normal plot of the regression standardized residual, okay, we can use the SPSS, for example. So this is most likely, okay, what you can observe in a normal distribution. So the normal distribution makes a straight diagonal line and the plotted residuals are compared with the diagonal. If a distribution is normal, the residual line closely follows the diagonal. So the same procedure can compare the dependent or independent variables separately to the normal distribution. Another assumption is that there should be no multicollinearity. Multicollinearity creates shared variance between variables, thus decreasing the ability to predict the dependent measure as well as ascertain the relative rules of each independent variable. Multicollinearity can have substantive effects not only on the predictive ability of a regression model, but also on the estimation of the regression coefficients and their statistical significance test. So remember that it's important for us to have a non-biased estimate of our coefficients because in the end, okay, if we will analyze our regression model, okay, the coefficient plays a crucial role in our analysis. So I'll show you that one later. So these are some of the remedies. Omit one or more highly correlated independent variables and identify other independent variables to help the prediction. The researcher should be careful when following this option. However, to avoid creating specification error when deleting one or more independent variables. So you should be careful, no? However, so to avoid creating specification error when deleting one or more independent variables. So sometimes it's not good to delete, okay, one or more independent variable. As much as possible, we are looking for a model that would help us describe the reality. And once we omit or delete a specific variable, especially if it's associated with a theory, so later, okay, it would be hard for us now to verify or to, expand the theory. So use the model with highly correlated independent variables for prediction only. make no attempt to interpret the regression coefficient. So while acknowledging the lowered level, this should be the case when you're acknowledging the lowered level of overall predictive ability. Use the simple correlations between each independent variable and the dependent variable to understand the independent-dependent variable relationship. Or finally, use a more sophisticated method of analysis such as Bayesian regression or a special case ridge regression or regression on principal components to obtain a model that more clearly reflects the simple effects of the independent variables. We will be discussing more of the principal component later. Sample size effects. Okay, another is, let's proceed to generalizability and sample size. This is another important concept in regression. So sample size effects or affects the generalizability of the results by the ratio of observations to independent variables. So the desired level is between 15 to 20 observations for each independent variable. So the result will be generalizable if the sample is representative. So if we follow this ratio, the result will be generalizable if the sample is representative. So you will work on your method of sampling later. So in order to ensure that the sampling is more, or the gathered sample is representative. But 15 to 20 observations would be fine, okay, generally. And that's the desired level. However, for stepwise procedure, the recommended level increases to 50 to 1 ratio because this technique selects only the strongest relationships within the data set and suffers from a greater tendency to become sample specific. So we have to use 50 is to 1 ratio in order for us to still, okay, ensure the generalizability of our result. Now, moving forward to types of linear regression, we have the standard method, which is, I think, the most familiar and the mostly or oftenly used by many users of statistical tools of regression analysis. The other one is stepwise, and of course, the other is hierarchical. Now, let's proceed to standard. Let's discuss the standard linear regression, which I think is the most familiar and quite familiar to everyone. So the simplest approach is to enter all of the predictors you have. So model in one step. So then generate the results using SPSS and interpret them. So this is just this is very simple. You just have to enter all of the predictors and run the SPSS if ever you're using your SPSS. And after that, you will have to interpret the results given by the statistical tools. Now, another is hierarchical linear regression. This approach is to enter your predictors in multiple predetermined steps. So this approach, or this is appropriate when you have meaningful groups of predictors. For instance, your predictors might include a few demographic variables such as gender and age, and personality characters such as extroversion and neuroticism. In this case, it might make sense to enter your demographic variables in one step and then enter your personality variables in another step. This would allow you see how much variance in your outcome, which of course your dependent variable, that the personality characters explain above and beyond the demographic variables. That's hierarchical linear regression. Another one is stepwise linear regression. Actually, this regression is a special case of hierarchical regression in which statistical algorithms determine what predictors end up in your model. This approach has 3 basic variations. We have forward selection, backward elimination, and stepwise. In forward selection, the model starts with no predictors and successively enters significant predictors until reaching a statistical stopping criteria. In backward elimination, however, the model starts with all possible predictors and successively removes non-significant predictors until reaching the stopping criteria. So this is contrary to the first one. No? So the stepwise regression, on the other hand, combines these 2 approaches, adding and removing predictors as it builds the model. So that's stepwise. So there are situations in which stepwise regression may be appropriate to use. For example, if you have a very large number of potential predictors to include in your model, so predictors may be reduced by using stepwise regression. It is usually better to narrow down the variables in your study based on the specific problem you are investigating and the background literature and theories surrounding the topic. If your research is purely exploratory and there's no existing theoretical foundation to guide the selection of variables, then stepwise regression may be applied as an exploratory analysis. So, okay, so let's use the standard. Let's interpret the results using, of course, these results was generated using the standard linear regression, not hierarchical and stepwise, but standard. So we have here the model summary, which we have R square of, or R of 0.426 and R square of 0.181. The ANOVA, which we have a sig value of 0. Okay, and the model, we have here the constant and the coefficient of autonomy, relatedness, and competence. So our dependent variable here is concealing. Okay, and we have our predictors, the autonomy, relatedness, and competence. So we have autonomy level, relatedness level, and competence level. And we also have concealing level as the dependent variable. So these are the coefficients here. Okay. The beta, 43.697, negative 2.385, negative 0.980, and 0.451 in competence, relatedness, autonomy, constant, respectively. So we also have the p-value. We have for constant, we have 0. We have 0.019 for autonomy. We have 0.384 for relatedness, and we have 0.618 for competence. Now, how good is the fit of the model? So to answer this question, proceed to the model summary. So we have here the model summary. Okay. Our R square is 0.181. So find the value of R, and it is 0.426. This means that 42.60% of the variability of concealing level, which is the dependent variable, can be explained by the predictors such as autonomy level, relatedness level, and competence level. So the higher or the closer it is to 1 or 100%, the better is our model. The best would be the fit of our model. So in this case, it's 42, it's barely 50, and even half of 100%. So I think it doesn't make sense to say that this is a model having a good fit. So the closer the value to 100, as I've said, okay, the better is the goodness of fit of the model. In this case, 42.60% is far from 100. So this established the idea that the generated multiple regression model does not have that high predictive capability as far as the chosen variables are concerned. So another question, does the coefficients of the model make sense? So with this one, we can look at the ANOVA table. Okay, here we have the p-value of 0 for our ANOVA table. So take note that multiple regression model for this problem should be in the following form. Y is equal to constant plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus n plus the error term, where y is the concealing level, x sub 1 is the value for autonomy level, x sub 2 for relatedness level, x sub 3 is for the competence level. B1 and B2 and B3 are coefficients. So these are important information in our variate, because they will determine how much is the contribution of x sub 1, x sub 2, x sub 3 to the model or value of y, because b sub 1, b sub 2, b sub 3, mathematically speaking, are the slopes of the regression line. So it will help us, or it will tell us if as the dependent or independent variable increases, will it provide how much value of increase or decrease to or how much value will it provide to the increase or decrease of the y variable, which is the concealing level. So it is important that b sub 1, b sub 2 should not be equal to 0. So the ANOVA table tells us if this coefficients, the b sub 1, b sub 2, b sub 3 is equal to 0. Since the null hypothesis for this is b sub 1, b sub 2, b sub 3 is equal to 0, and the decision rule is to reject the null hypothesis if the p-value, which is the sig, is less than alpha is equal to 0.05, we will use alpha 0.05 in this case. So from the ANOVA table, p-value of the sig is 0.00. Thus, the p-value is less than alpha, which is 0.05. Therefore, we must reject the null hypothesis, okay, in favor of the alternative hypothesis, telling us that b sub 1, b sub 2, and b sub 3 are not equal to 0. So we are confident that our coefficients are not equal to 0. So we can use the model for prediction purposes. So if the coefficients are not equal to 0, then how statistically significant are they? So this time, you must consider the table of results for coefficients. Okay, so since our coefficients are not equal to 0, okay, so let's proceed to the table for coefficients here. Okay, the third table here at the bottom. So look at the coefficients, the B, unstandardized coefficients. So constant is equal to 43.697. The B sub 1 is equal to negative 2.385, and B2 is equal to negative 0.980, and B3 is equal to 0.451. So null hypothesis here is that the coefficient is not statistically significant. Decision rule, reject the null hypothesis if the p-value or sig is less than alpha is equal to 0.05. Now, in the table of results for the coefficients, only the coefficients for the constant and the autonomy level have p-value or sig less than 0.05. Thus, only the coefficients for the constant and autonomy level are statistically significant. So, this is our final model, okay? Where y is concealing level, our constant is 43.697. So, this is the concealing level if ever there's no autonomy, relatedness, and competence level. So the concealing level would be 43.697. That's a constant. And we have minus 2.385. This is our beta or B sub 1, our coefficient for autonomy level. Minus 0.980, our coefficient for relatedness level. And 0.451, our coefficient level for competence level. So what if autonomy level increases by 2 units? What will happen to the value of concealing level? Now, this is what happens, okay? So we will just place the value of 2 units, okay, to autonomy level. Okay, so here, we just have to place 2 to our x sub 1. Or x1. So that's negative 2.385 times 2, and that would give us negative 4.77. Therefore, this means that if autonomy level increases by 2 units, the concealing level will decrease by 4.77 units. This means that the higher level of autonomy will substantially decrease concealing level. So that's all. I'll be discussing more about, or I'll be providing more materials for the different types of multiple linear regression, the hierarchical, since we know the standard already, so we will proceed to hierarchical stepwise, and of course, the specific flow of using SPSS, okay, for the assumptions or testing the assumptions. Okay, so I'll be providing materials for those topics or concepts. That's all. Have a great day ahead.